what I'm going to say is that I'm going to try to tell the story of an obsession, right? An obsession that the entire team and I have about trying to create better merging and diffing, right? So before I start, I'm going to share a little bit of who we are, right? As we said before, we've been in business for 13 years already, doing version control. We are a small team of 17 people. We are located here, based here in Spain, although we have customers all around the world. Our main thing is plastic SCM. We develop a version control. It's not based on Git. It's a completely different stack. But we also develop GUIs, server-side, and then tons of merge tools. Well, different merge tools, which is the thing I'll be focusing on today. And then we have developed something we call semantic diffing and merging. And we put all together into a Git client, which is what drives the entire story I'll be sharing now. So what is this session all about? This is the agenda I have. I'll first start by, well, making a question. Is text diff and merge the end of the trip? Is the end of the story? As I said, we have an obsession with that. I mean, we really want to come up with something different. This is what we've been working on for the last few years. So we think it's not the end, right? So we think there's more on that. Well, after that, I'll be sharing a few numbers of some experiments we ran, so we give you a little bit of context. Then I'll be walking through the different steps we went through over the last years, like the first initial approach, then really going semantic, and then going multi-file. So I hope it's as interesting for you as I think it is. So first of all is what we mean by semantic, right? Just to give you a little bit of context. OK, look at this sample. This is the base of a merge, how a file was. And we have a method there. This is coming from leaf git 2 sharp. And OK, we have a remove method there. And then someone makes a modification to this method and moves it up in the file because he thinks it's a better idea to have it sorted on a different way. And then in parallel, someone else modifies the method too and moves it down. What happens when you try to merge this with a traditional three-way merge tool? OK, normally, except if I did something wrong, you wouldn't have any conflicts, and you end up with 3 copies of your method. Probably it won't compile. Well, it won't compile. And, well, it will go, OK, it was merged probably even automatically, and you end up with something that doesn't even build. Well, this is what we consider a semantic issue. Probably syntactic will be better, but semantic is like a bigger word, so we like it better. So, and that's it. So, a few numbers. OK, how it goes. So we've been running a few thousands experiments on what we call merge replay, which is, OK, we download like a few, I said more than 1,000. I think we went beyond that. 1,000 GitHub public repositories. We download them. We walk the DAG. And I think we do walk the DAG backwards, so sorry for that. So, and what we do is reply the merge. Like, OK, we get the destination of the merge, we go back, and then we reply the merge and try to reproduce it, right? And what we found out is that about when you merge branches, like 50% less of manual conflicts are needed, which means we are trying to really avoid manual intervention, which is what really scares you off, right? So full branch merge means all the files in the merge can be automatically merged, or they are in conflict 15% less times than done with the regular merge, right? And if you go for individual, and we think this is very interesting because it means a lot of pull requests that are now that now they need manual intervention could be fully automated. That's a good number, right? And then there's even a bigger number, which means that even if your branch cannot be fully merged, still many of the files inside in conflict can be automatically merged by this approach. And we found out like 32% less in average of merges of individual files need manual intervention following this approach. OK, this is the end unit repository. And of course, what I shared is the average, but the average was sometimes not as good as we expected, so we shared this number, which is much better. And okay, just to give you an idea, I mean, in some repos, it can get even better. As you can see here, is almost 37% of branches being completely, 37% less of manual intervention on branches. Okay, we created a small analyzer that you can check later. It's a really simple thing. You just submit your GitHub repo, and it tells you how much time or how many merges you can actually automate by using this sort of approach to merging. Okay, if you have lots of CML files and not really the source code we support, then you will get better results, but that's the idea. Okay, so now a remark, right? I mean, I'm like starting from the results, and now I'm going to show you the entire train of thought we followed. One remark: all this happens even when we all try to avoid doing refactors while someone else is touching the same code, right? And it still happens. So our vision is that someday, if we all take advantage of this approach to diffing and merging, it will happen more and it will be automated more also. Okay, so this is how we started, finding moved code through fragment similarity. We call it cross-diff and cross-merge because we like cool names, as I said before. And okay, what we do is we calculate the diffs, how it works, right? What we did, and we started, we had this for years already, we started long ago. What we do is, the technique goes as follows. We calculate the diff, and then we try to match added and deleted blocks. So whatever is added and deleted is a potential candidate for a move. And this is how we track moved code within a file. The nice approach, and the similarity algorithm we use is something very, very similar to what Git uses internally to actually track move files and so on. So it's almost the same approach. And well, then we have a challenge in GUI space, which I show, one of the solutions, because you have to represent that so the user really understands it, right? So for merge, it does something a little bit more tricky, which is it calculates the candidates. Like, okay, if you move some code to a different place in the same file, within the same file, what happened if someone else also modified in the original or something like that? I'll show you it with an example. Well, the benefit of this approach, which was our original approach to the problem, is that it's code agnostic. It works for C#, it works for C, it works for love letters, it works for whatever, right? It doesn't care about the actual language underneath. This is a screenshot, a very old one, of cross-diff. Like you see, it's a fragment of code being moved, and well, we paint somehow a line saying it's the same thing. The detection is the important thing that I want to share in this session, and it's like, well, what I explained before, right? Like matching what was. You see, there's a block being deleted. There's another one being added, and then it's matched because it's quite similar. Then, for merge, it's slightly more complicated. It's still a very manual process, but it can help in certain cases, not in all cases, but in certain cases. This is a typical example. What you have on the center is the base, the ancestor, how it was, then one contributor and the other. And this is a typical case for what we call the cross-merge. And what happens is, okay, you have some code that was modified, and then on the other contributor was deleted. Chances are, or we think this is a good heuristic, chances are the code has been moved. So we show an action on the screen saying, okay, you can cross-merge this. And when you click on this, it will say, okay, you know what? I find a similar fragment of code in a different place. So you can go and pick up the 3 fragments, merge it. This is what we call submerge, because you pick up the fragments, merge them with a 3-way merge tool, and then put the result on the destination. This was our first approach, right? And we use it for years. It's not magic. I mean, it doesn't work in all cases, but we thought it was great at the beginning. Then we went for what we said it was the semantic approach. As I said, it will be more like a syntax-based thing, and here's how it works. We start with a file, and then we parse it, and we create a tree. It's not like an AST, because it's a little bit simplified. Basically, all we care about are the positions of the declarations within the file. As you can see here, we have an add method, and then all what we care about is the position, what it is, where it ends, and so on, right? So we parse the code, we create a tree, and we will work based on that. Actually, the format is a little bit more complicated, and here is one of the places where there's a lot of room for improvement for us, because instead of storing like only where it begins and it ends based on row and column, we just we make the guy doing the parser actually count the characters, which is a little bit painful, but it works. In fact, we have ways to create external parsers, so anyone can write their own. Some community members did like support for Delphi and F# and a few others. So that's possible, right, to do. So as soon as we have the tree, the simplified tree of the structure of the file, what we do is try to match the nodes, right? Like, OK, I parse the two versions of the file, and then I start with the first method called add, and I try to find it in the other version, in the other tree. If it's there, it's a match, nothing happened. If you don't find it, you mark it as at least temporarily removed. And then the same happens with added methods and so on. In order to match, we follow a very simple approach, which is, OK, same method name. If the bodies are the same thing, then it's the same method. If the bodies are not exactly the same, then we, again, reuse the previous code we did for the X diff, the cross diff, which is, OK, how similar they are. So just to make it clear, what we do is that we stop at the declaration, at the method level, or the function, or the declaration. I mean, we don't parse the ifs and else and fors and all that. I mean, we treat the bodies as text. So we get the structure, everything else as text. So what's the nice thing with this way of diffing? OK, you move a method to a different location. We still know it's exactly the same method because it's very similar and so on. We can also track renames. Like if the bodies are the same and the method names change, well, it was modified, right? So that's how it works, right? That's the second approach we had, right? So what happens to merge? Well, we reuse the diff again. Well, the nice thing with this is that you can go reusing step by step and building on top of the last approach, right? So what we do for merging, very simple. What we do is we parse the three contributors, and here what we do is if you invoke the tool with Git, as soon as you do Git Merge tool, our tool will get the three contributors. We parse the three of them, then we get the three trees, and then as soon as we get the three trees, we run the diffs, and then we get two pairs of diffs, and then we actually try to merge based on the tree structures. Here, we reuse a lot of the work we previously did for files and directories with our own version control implementation, right? So a lot of the work we've done there, or at least the knowledge we got from there, we applied here. So we start calculating different types of conflicts. And some of them are, I'll explain a few of those, right? But some of them are things like cyclic move, divergent move, like what happens if you move the same thing to two different places in parallel, like the one you saw before, evil twins, which is, again, a pretty cool name, and then specific constructs. Like, for instance, suppose you have, well, we develop mostly in C#, and although I love C, but anyway. So suppose you add a using, and someone else from the team adds exactly the same using 3 lines below that. Well, it's very, very simple to know this is a using, so it's not even a conflict. You just keep one of them. Automatically solved, right? It's not a big deal to solve it manually either, but it can do it this way. So a few of the conflicts here. Well, and this is what names actually my session, because this is my favorite merge case. Look at the scenario. You have a class which is like a socket implementation with listen and connect and so on, and then you decide to refactor in 2 different ways. You want to create something called client socket, and then another thing called server socket. This is the base. This is what one contributor did. This is what the other contributor did, right? With the semantic approach, this is an automatic merge, no conflicts. Why? Look at the annotations. None of the methods has icons. Well, I use icons, it can be whatever else, anything else, right? On the two sides, so there are no conflicts at all. If you try this with a regular text-based approach, what you will get is the code trying to match get host by name, which was modified in one contributor, trying to match it with the declaration of the server socket. So, you know, sorry, with recb, most likely. So you'll be hitting something that doesn't make a lot of sense. I mean, you'll have tons of conflicts in an scenario like this, and it will be a little bit complicated to solve. With the semantic approach, it's automatic. You will get the 3 classes. I mean, you will even get the rename of the old socket class to DNS and so on, completely automatic. OK, the other default twin, also very common. Someone adds a class. There's nothing, no modifications or anything, but sorry, a class, a method, and someone else adds another method on a different location. Again, using the semantic approach, instead of duplicating and then detecting it during at build time, the merge is smart enough to actually figure out it's the same thing, so it keeps just one of them. Which one? I think the current heuristic we use is like, I don't know, the first one it finds by position or something. It won't affect the build, so it's OK. OK, and then my second favorite, which is divergent move. OK, I started where I finished with my previous socket example. Then I have the listen method. And then what happens if I move it to client socket again? It doesn't make a sense at all to move it there, probably. But you know, it's just for the sake of the example. So one developer, one contributor move it to one location, while someone else move it to a different location. It's still happening within the same file. Well, what you will get here is, instead of a lot of conflicts, the tool saying, well, the tool can detect that is the same method that was modified in 2 places, and that you have to choose whether you want it in one location or the other. So what you will expect here when you solve this is like, OK, where do you want to put it? And as soon as you decide on the structure conflict, it will say, OK, now I merge the content. And then it's a simple 3-way merge. OK, so the thing here is that everything I explained so far happens within a single file, right? But the real stuff, the real thing we wanted to do from the very beginning was to really implement this cross-file. And this is where some of the challenges started. And well, that's what I'm going to share from now on. OK, so multi-file, as I said, was the goal from the very beginning. But for all the previous steps, we could rely on being invoked as a regular 3-way merge tool. Like you configure your Git, and instead of calling, I don't know, kdiff3 or whatever, you just invoke our tool. You get the 3 contributors, and you're done. But in order to do real diff and merge for multi-file, you need a different approach, because you need more information. And that's what I'm going to explain. Basically, well, we call the diff, the cross-file diff, we call it refactored detection. That's something we also like. We need deeper interaction with the version control, so it's not version control agnostic anymore. And this was one of the reasons that triggered us to start last year developing a new Git client, right? Which is this gmaster that we've been working on for the last few months. OK, so this is a cross-file. What it does? Well, this is an example I'll be following for the next minutes. So basically, you have a class called period, and then you have a method, GetTimeBetween. The other one is just making noise to make it more interesting, but the real thing is here. And then it's being changed, moved, and renamed. And the move has happened to a different file, and it can be detected. In fact, this graphic here is actually taken from the tool itself, right? So how we calculate it, because that's the part of the story I want to focus on. Well, we calculate it on the following way. Basically, we parse each of the files on the commit you are diffing, right? That's the first thing we do. So we parse each file. We calculate the diffs for each of the files, and then we have some added and deleted methods. And when I say method, because I'm more on the C#, it can be functions or anything else, right? So once you get the list of your added and deleted declarations, we try to match them across files. Everything before happened on a single file. Now we get the list, and we try to match them, following exactly the same heuristics we did before. Like, OK, match the contents, content similarity. We do some tweaks here and there with arguments of the methods and things like that, right? And, well, of course, for us, the devil is in the details. I mean, it must be fast enough. I mean, the overall explanation is exactly what I told you, but then there are, as you might imagine, a few details here and there. So later on, once you have that, we can call something we call the subdiff. So you can click and actually diff the same method even across the different files. And you just get the two fragments and call a standard diff, right? Text-based diff. Pretty simple. So that's what we call the refactor detection. OK, so let's focus on this poor method, GetTimeBetween, which was renamed to UnitsBetween, and what happens if someone else modifies GetTimeBetween in parallel on a different branch. That's where the real thing comes. Well, here is a branch diagram, and this is actually what happened. Here is the commit where I detected this refactor, moving a method to a different file. Actually, I move it from period.cs to timeperiodfield.cs. But then here, someone else from the team in parallel decided to actually modify the original method on its original location. Okay? So when you want to merge this, as I said, you need more info for the version control. Why? Because when you merge that, OK, you ask Git to merge this, and then it will probably detect a conflict on period.cs because it was modified by the two contributors. But the other file, time period field, is not in the index because not in conflict. It was modified before. And this is where the real thing comes. This is where we need deeper integration, and that's why being an independent merge tool wasn't enough for our initial approach. If we run this from our own client, what we do is not only use it as merge tool. We drive the entire merge. We ask the libgit2 to actually do part of the merge. And then we say, hey, we have all these differences on the index normally. Well, they are there, actually. And then we need to diff destination and base. We do that to actually get the other files involved in the merge. They cannot be in conflict, or maybe they are not in conflict, like in this case, but they can be involved. Then, once we have this list, we'll get the two files we need, period.cs, that was on the index, and then time period field, which wasn't. Then we parse them, and then we calculate the diffs for each of the contributors, like before, like with the base and so on. And then we get the entire trees of all the contributors, and we start doing all the diffs. Well, as I said here, the Git status was not enough because it's not in the index, and then we need to get this extra info. OK, well, that's just exactly what I explained, that we need to diff the destination versus the base, and time period field is not in conflict, but it's involved. So how multifile is calculated? As I said, we parse all the involved file. By involved, we mean what I just explained, like everything in there. Then we calculate the merge based on that. And it is, again, like an individual file merge, like an individual semantic merge. You go just trying to calculate all the conflicts and so on. But then all the added and deleted, that's the magic always. All the added and deleted are move candidates, even cross-file. And that's what we calculate. How it looks like? It looks like this. This is an actual graphic you can get, which is, I mean, when you have like sample classes with 3 methods, it's very nice to see. When you have hundreds of them, it's a little bit more complicated. But as we saw before, with solid principles and so on, you should have so many methods. Anyway, so, well, that's actually the conflict that we represent. This is actually what we show to the user, but it's also a representation of what's going on behind the scenes. Because what we get is GetTimeBetween was modified, and so on. What you get here, well, the next challenge for us, once we detect it, and that's something we struggled with for really a long time, was how to show that to the user without, driving him crazy or something like that. So once we do that, basically, what we have to do is, OK, first, let him decide, OK, you need to merge this, you need to solve the conflict, and then it's going to be incorporated here. That's the simple part. The good thing is how to represent it. So as I said, we struggled with that, and then we went for different alternatives. I'm going to explain one of the first ones. This is not even the tool itself. This is like Visio drawing and Paint. So what we have at the very beginning with a special with the first approach was like a very alien solution. Like, OK, we show all the conflicts, and then we show diffs and so on. But you really, except if you get this view, you really didn't get what was actually happening, right? And then the first version we released actually a few years ago of the merge solution, even before going multi-file, looked more like this, right? What we actually decided now was to decorate the standard three-way merge with the annotations of the, well, the multi-file stuff. And that's what comes here. Basically, what you get is you are merging the file with the conflict, which is time period field. And when you're merging that, it tells you, OK, you have a method here. It's normal, no conflicts or anything, because the method was just added in the contributor. But it's decorated because the merge tool is having information not only of the 3 files involved in a regular merge, but all the files involved in the multi-file, right? Once you get that, it can tell you, well, this method is special because the underlying data that is telling you it's been moved and so on. So you go, click to merge it, and what you get is the other contributors, the other contributor that is on the other file, right? Or was on the other file. So the end result is that you get the change made in parallel by your colleague here, incorporated in the final version, you move to a different place. And that's what the multi-file semantic is all about. It's still not, we can detect different types of methods. It's still work in progress. We have several things to improve. I think there are some divergent move cases we are not handling like 100% perfect so far, but we are there, and there are different types of conflicts to solve. And that we detect. One of them, as I said, is a divergent. Like you move method to different locations, you have to choose. Not like the one I show you. You have to choose which one you want, and then you merge it. But it's also very helpful in a very simple case, which is when you just move something to a different location. In the location there, you have to incorporate original changes like I showed before. So what is next for us? Well, there's something I forgot to say. Even on a single file conflict, on a single file merge, if you have conflicts on a method, it can be that the method could be merged automatically, but you want to review it. Like the typical example where something is modified at the beginning of the method, something is modified at the end. With a semantic approach, you can mark it as a conflict if you want to ensure it's always reviewed, right? OK, so ideas we have for the future. Some of them we've been working on. Some of them are just wishful thinking. Semantic blame, like, OK, you go blaming, but actually tracking all the move code, even across files. The cross-file semantic blame, as I said here, that's something we never try, but it's always like on our minds. Method history, this is very good for C#, Java, and so on. Like you right-click on a method, and you show the history of this. You basically go back parsing all the versions of the file and showing exactly what it was. So if it's moved or anything, you are not affected by that. Then track extracted code from methods. That's something we didn't think about it yet, how to solve it, but it will be interesting. Like we are working on a method-by-method base right now, but what if you extract part of it to a different location, something that is on our roadmap? And then support for more languages. Like right now, we're doing out-of-the-box C#, C, C++, and Java, but we would like to extend it to others. And then also support different types of files. Like in the .NET world, there are sometimes conflict in .csprog and stuff like that, so doing this kind of stuff. So that's basically our trip through the semantic diffing and merging and trying to do really difficult merges automatic. Thank you.